Good morning, everyone, and welcome again to our seminar series, Circuits, Terahertz, and Beyond. I'm Ted Rappaport, the director of NYU Wireless, and on behalf of the NYU Wireless Industrial Affiliates, who sponsor our lab and help us bring research to the wireless industry, and the Electrical and Computer Engineering Department here at Tandon School of Engineering, it's my pleasure to welcome you to our 6th exciting seminar in our seminar series. Today, we're very fortunate to have with us Professor Harish Krishnaswamy, who's from Columbia. And Harish is actually a pioneer in millimeter wave circuits. I met him over 10 years ago at the Premier Circuits Conference, ISSCC in San Francisco, where he had won the Best Paper Award for millimeter wave circuits. This is before anyone believed in millimeter wave, so really we're a pioneer there. He's gone on to build a huge lab at Columbia, so he hasn't come far for this talk. And we're very fortunate to have him because he's involved in a lot of the major wireless research initiatives here in New York City, both with a large SRC jump project that NYU Wireless is part of, and also the NSF Power, the Platform for Advanced Wireless Research. Please give Professor Harish a big warm welcome from NYU. Thank you for coming.
Thanks, Ted, and good morning, everyone. Thanks, Ted, and good morning, everyone. It's a pleasure for me to be here today and to talk to you about my research. So this talk is titled Enabling the Third Wireless Revolution Through Transformative RF and Millimeter Wave Circuits and Systems for Wireless Communications and Sensing. So before I start this talk, I usually like to give a shout out to my PhD students because really it's all their work that goes into this presentation. I run a research group. We call ourselves the Columbia High Speed and Millimeter Wave IC Lab, or COSMIC Lab. And currently we're about 12 or 13 people, postdoc and several graduate students. We have 7 PhD students who have graduated from this lab. Many of them are at research labs at various industrial locations, as well as within academia. We have a student who's an assistant professor at the University of Illinois, and a current student will be joining MIT as an assistant professor next year. But wherever they go, my hope is that they're really continuing to pioneer wireless research wherever they are. I'd also like to acknowledge the various sponsors that have gone into that have supported this work. A lot of our research is supported by DARPA, so a lot of the millimeter wave work as well as work down at RF has been supported through various DARPA programs over the years. But we're also fortunate to work with several industrial partners, including Qualcomm, Intel, Texas Instruments, Huawei, etc. So this is the outline of the presentation. So let me talk a little bit about what I call the third wireless revolution and what my vision for it is. And then I'll talk a little bit about certain specific areas of research that we've looked into that play a part in enabling this third wireless revolution. So I'll talk a little bit about millimeter wave with a focus on high power and high efficiency. I'll talk about non-reciprocal components. I'll talk about full duplex. I'll talk about massive MIMO. If you see a theme here, these are really a lot of the candidate technologies that are a part of 5G and potentially 6G. So we have a heavy focus within my group on emerging wireless communication technologies. And then I'll talk a little bit about some future research directions that we're starting within the group. So we've all heard a lot about the big data revolution. What I'd like to comment on, and I think this is something that folks here would obviously be very familiar with, is that wireless plays a very big part of the data revolution, because ultimately the data that is generated at certain locations has to be moved around, and a lot of that is done wirelessly. If you look at the total amount of wireless data that gets transported per year, that tends to grow exponentially over time. And this is really being driven by the fact that we've now evolved to a place where smartphones and tablets are our dominant personal computing devices. They've replaced laptops and desktop computers, which are really a thing of the past. And we're using these mobile devices for really high data applications such as streaming video, et cetera. And that's what's really driving this enormous growth in wireless data capacity. Now, to support this enormous growth in wireless data capacity, let me actually skip forward here and talk a little bit about these emerging wireless paradigms. We've started to look at new forms of wireless communication. So millimeter wave is a new form of wireless communication that exploits a region of the spectrum that's an order of magnitude higher than what we've traditionally used. And by going to higher frequencies, you get higher bandwidths, which can be used to transport more data. Aside from millimeter wave, there's also been a lot of investigation into other new ways of communicating, including full duplex, where you transmit and receive at the same time, at the same frequency, potentially doubling data capacity, as well as using a very large number of antennas in massive MIMO to simultaneously communicate with a large number of users at the same time, again increasing capacity. And so really, 5G technology is targeting 1,000x increase in data capacity and is really leveraging a lot of these emerging wireless communication concepts to deliver that 1,000x. So now let me move back here to talk a little bit about this third wireless revolution. So when I think about 5G and potentially 6G, I'd like to think about what wireless has done for us in the past. So in the 1990s, we essentially went through the first wireless revolution, which was essentially about mobile wireless communication. So for the first time, we really had cell phones in everybody's hand that enabled people to immediately communicate with people across the world instantaneously. And it was about connecting with other people, essentially. And you could do that while you were on the go. Then when you look at the next 2 decades, roughly 2000 to 2020, and this is roughly contemporaneous with 3G and 4G really rolling out in a big way, and to a little small degree, the early stages of 5G, this was really the mobile wireless data revolution, which now meant that at your fingertips, you had immediate access to the internet. You could use your mobile device to get online, to connect to the internet, and any amount of data that was available on the internet could be immediately accessible to you. Right? Essentially, wireless communication technologies reached that level of maturity. You had that level of bandwidth that you could immediately get access to any amount of information on the internet at your fingertips while you were on the go. So what is the third wireless revolution going to bring? So my vision of the third wireless revolution is that it's the era of mobile wireless reality. And what I mean by that is now wireless will allow us to interact with the physical world in new ways. So what I mean by that is if you imagine this room, for instance, you imagine the 4 walls of the room, you imagine these, the texture of the room, the wooden panels, etc. There's a lot more information just in this room, in the structure of it, than the entire internet, by far. If you think about exact locations and positions of various objects, what they are made of, there's a lot more information in just this one room than the entire internet. And what wireless will enable us to do is interrogate that physical world in new ways. And so that means things like using wireless for gesture recognition, using wireless for extremely accurate positioning, using wireless for sensing materials, using wireless for 3D video, virtual reality, vision quality imaging for the first time, wireless imaging that reaches the quality of actual vision. And so this is what I think the third wireless revolution will bring for us. And this is certainly way beyond 5G. This requires pushing into new frontiers of frequencies, the terahertz frequency domain. It requires new architectures, new communication paradigms. But this is really what I think we should be thinking about when we think about the next generations of wireless technology. Another way to think about that before I move on is we should think about wireless as basically enhancing our human sensory perception. So, we are imbued as human beings with certain senses, with vision, with touch, with auditory senses. How can you use wireless to expand our sensory perception of the environment around us in essentially new ways? Now, delving down into actual hardcore wireless topics, what does this really require? So as we move towards these higher frequencies in 5G and potentially 6G, we're talking about much higher data rates. We're talking about very high spectral efficiency. But one open question that I think everyone needs to solve, whether it's at the device level, the circuits level, or the systems level, is what's the energy associated with that type of communication? So is it possible to have very high data rate, spectrally efficient communication while also being energy efficient at the same time? Can you cram in a large number of bits in the spectrum that you have per hertz, but consume very few nanojoules per bit? And historically, this has not been possible. So if you look at existing hardware for wireless technologies, whether it's your legacy Wi-Fi devices or emerging devices for 60 gigahertz or in the W band, these tend to populate the regions where the spectral efficiency is low and the energy efficiency is also low. Or if you go to high spectral efficiency, you're also forced to consume high energy per bit. So populating this region where you can cram in a large number of bits, but you're not consuming energy to do so, still is a very open problem. Now, when I think about my research and the kind of philosophy that we apply to hardware to enable this, we really think about signal processing at various different domains within a radio. So when you think about a radio, it has 4 domains. You have the front end. This includes things like antennas, filters. Then you have the RF domain, where you build blocks such as low noise amplifiers and mixers. Then you have the analog domain, and then you have the digital domain. Historically, the front end domain has been one where your tools and techniques are electromagnetics, acoustics. The tools and techniques at RF are things like circuit design, chip design. Once you start to move into the analog, you're starting to do more sophisticated signal processing. You do a little bit of equalization, you do a little bit of filtering. Then when you move into the digital domain, you start to do more advanced signal processing functions, interference cancellation, more advanced equalization techniques, and so on. So one approach that we have been taking on the hardware side as we think about millimeter wave, in general, in new forms of wireless, is can we blur the boundaries between these different domains of the radio? Can we think about moving signal processing functionality that you historically did in the analog and the digital up into the RF, maybe even into the domain of electromagnetics? Can we think about doing signal processing in electromagnetics or at RF? And this is certainly not an original or new idea by any means. There's been a lot of work in the RF community on software-defined radios where essentially analog signal processing functionalities are now being done at RF, even at the antenna interface. What we've been really pushing towards is, can we even do things that were historically done in digital, such as interference cancellation, equalization, et cetera? Can we move that into the RF, maybe even into the antenna? And the argument is that this is the kind of thing that you need to do to enable new forms of wireless communications while not breaking the energy bank, per se. So now let me talk about some specific examples. So I'll talk a little bit about millimeter wave. Since I'm covering sort of the breadth of the work that my lab does on each of these topics, I'm only going to have a couple of slides. I won't get into a lot of detail. It's mostly to give you guys a flavor of the kind of things that we do. And if you have any questions, I'm happy to take them offline and go into additional detail. Also, as I go through these slides, there'll be references to some of our papers, which you might find interesting. So at millimeter wave, I would argue a lot of the fundamental work on chip design for millimeter wave was done in the 2000s. In the 2000s, 60 gigahertz was a big thing. There was a lot of interest in the mid-2000s on this unlicensed band that people thought were going to be the third tier of Wi-Fi. A lot of folks, including myself as well as other colleagues at the same time, we got our PhDs doing that. There were startup companies and so forth. Never completely took off. We still don't see 60 gigahertz in a big way in the market. But in that effort, a lot of the circuit design work in building things like amplifiers, phase shifters, mixers, oscillators was done. And I would argue there are no new problems to be solved on that front today. The one open problem, in my view, at millimeter wave is generating power. So you need to generate power in a power amplifier to communicate over long distances. And fundamentally, when you go towards higher frequencies, the power that you can generate drops off. You can show for any electronic technology that as you go up in frequency, the power that can be generated from that device falls as 1 over F. So for every decade in frequency, you take a 10 dB hit in output power. And so while at lower RF frequencies, under 10 gigahertz, you can easily generate 1 watt of power at millimeter wave, at RF in CMOS. When you get to millimeter waves, you're looking at amplifiers that can generate 10, 20, 30 milliwatts of output power. The efficiency with which you can generate that power also tends to drop off. Efficiency is a more complicated phenomenon because there are losses in various, in both the active devices and the passive devices. So it isn't easy to derive a very simple 1 over F kind of dependency. But again, you can see that while at RF, sub 6 gigahertz, which isn't plotted on this chart, people have shown efficiencies of 40 to 50% in amplifiers. When you get towards millimeter waves, you're really looking at the 10, 15, 20% efficiency levels. And this is still a problem today. It's an unsolved problem. This raises open questions as to whether large-scale millimeter wave mobile communications, even for 5G, can be really viable. Can we cover cell radiuses of several hundred meters? Can we overcome blockage from foliage, from human beings? This is still an open problem. So this is something that my group worked on for several years. There was a DARPA program that was essentially chartered with pushing millimeter wave power amplifiers from the 10, 20 milliwatt range to the 1 watt range. Can you generate a watt of power at millimeter wave the way you can at RF? So we worked on this problem. We used a technique called stacking in silicon on insulator CMOS. Essentially, the problem is when you look at a single device can handle a very small voltage before it will break. But if you can stack devices, you can add up the voltage of the different devices so that the final voltage that you get that you deliver to your antenna is linearly larger than the voltage that a single device can deliver. So if you stack 4 devices, you get 4 times more voltage, 16 times more power. And so that's where an order of magnitude benefit in output power is derived from. So, at this level of description, it's a very simple idea, right? I mean, it sounds almost trivial. Of course, at millimeter wave, nothing is easy. A lot of the intellectual work that went into this, that went into that DARPA program, not just from my group, but also other researchers at the University of California at San Diego, for instance, is how at millimeter wave do you get these voltages to add up exactly at all of these intermediary nodes. Do you have parasitic capacitance that causes the voltages to phase shift? Then they don't add up correctly. You get destructive interference. So a lot of the circuit design tricks went into solving those types of problems so that you could get the linear addition and the quadratic increase in output power. So we showed if amplifiers with output powers as high as 17 to 23 dBm, so that's like 15 to 200 milliwatts of output power, depending upon how many devices you stacked, and the efficiencies could be as high as 35%. So at the single amplifier level, this was close to an order of magnitude higher power and somewhat like 2 to 3 times higher efficiency.
What do you think it needs to be for commercial viability? Can you repeat my question?
Yeah. So the question is, what does it need for commercial viability? So actually, it's a good question. I'm actually involved with a startup company that is trying to commercially commercialize this technology. Actually, people will accept that the stacked power amplifier is the highest performing PA out there. So that is, I think, an accepted fact. What this really needs is for the ecosystem around SOI CMOS to kind of develop further. So if you look at, so what allows us to do this is we use a flavor of CMOS called silicon and insulator CMOS, which allows you to float the voltages up to these higher levels and without breaking down some of these intermediary node junctions. And essentially, this is a technology that, for instance, is offered by Global Foundries as well as some other foundries. And what is really needed for this technology to really flourish is for SOI CMOS in general to flourish and for this kind of a technology to become mainstream, to have large volumes of products shipped in that technology.
Is 35% the right number, or should it be 50%?
I think 35%, so one point that I would make about the 35% number is this is a peak efficiency. What you really care about is efficiency under modulation. That number tends to be, depending upon what you do, more like 20% or thereabouts. I think there's certainly room to improve that, and there's active research going on PA architectures that can enhance efficiency under modulation. So that is an open problem. In relation to that, what I would say is that a lot of those architectures that you would use, like Doherty, that enhance efficiency under modulation, they increase the nonlinearity. So if you need to use digital predistortion to linearize those, then that's basically hiding the problem somewhere else, especially in an array architecture where it's not possible to have digital at every single element to predistort each individual PA. So I would say architectures that can boost efficiency under modulation while not requiring digital predistortion is sort of the name of the game. We also looked at power combining. This is not necessarily a technology that would be used in an array setting, but just to try and prove that we could get to a watt of output power, we took a bunch of these stacked PAs and then we combined them with a low-loss combiner, and we were able to show saturated output powers as high as half a watt, which I think still today stands as the highest output power that has been generated at millimeter wave from a CMOS PA. Now, these power combined amplifiers tend to be fairly large in size. You can't use them further in an array setting, but this was within the context of a DARPA program, which was trying to essentially show that you could get to a watt of power in CMOS, and that is actually viable. Plus, these types of power-combined PAs with high output power would be useful in wireless links where a single PA is driving a high-gain directional antenna. This is really targeting a SATCOM application, which is how, in SATCOM, those are how those systems are architected. So that's all that I'm going to say about some of that work. But if you're interested in some of this PA work, please feel free to go and take a look at these papers. These are a little dated right now. So this power amplifier work was done about 5 years ago or so, and we really haven't been working on this problem since. But certainly other researchers in the community have been. And so there's a slew of PA papers that actually look at efficiency under backoff and things of that nature that are coming out in the last 2 or 3 years. So now let me move on and talk a little bit about full duplex. So we've also heavily been working on full duplex. I think there's activity here at NYU on that topic as well. So I think several of you would know what full duplex is about. For the benefit of the audience, I will just say a couple of quick words. All of today's wireless communications are half duplex. Basically, transmission and reception are either separated in different time slots, which is time division duplex, or they happen at the same time but at different frequencies, frequency division duplex. If you could transmit and receive at the same time at the same frequency, then you can potentially double capacity immediately. You also offer several other advantages that are useful at the network level. The big challenge with doing this is, if you're transmitting at the same time as you're receiving, then your receiver will be operating in the presence of a huge interference or echo from your transmitter. And if you compare the, let's say, 1 watt-ish type of power that your transmitter is producing to the -100, -110, -120 dBm type of power levels that the receiver is trying to receive, we're talking about more than 100 dB, more than 120 dB even, a factor of 1 trillion difference between your interference and your desired signal. So you need to suppress or cancel that transmitter interference to the tune of more than 100 dB. Now, for those of you guys who have ever built anything, 100 dB of anything is very hard, right? 100 dB, whether it's interference cancellation, dynamic range, anything, 100 is just a lot of dB. So the only way to get 100 dB of anything is to get it in multiple stages. Getting 100 dB in one stage is nearly impossible. So you need to essentially have multiple stages of interference cancellation, and if you can get 30 to 40 dB in each stage, then the net interference suppression can reach something like 100 dB. And so all the work in full duplex uses some isolation at the antenna, some cancellation at RF, some cancellation in analog, and then some cancellation in the digital domain. And with these 4 layers of suppression, maybe you can get to about 100 dB of interference suppression. But more than just this 100 dB, there are several other challenges associated with interference suppression. One issue is that the interference from the transmitter to the receiver, it leaks through a direct path between, let's say, the 2 antennas that you're using, but also you have reflections from the environment. And so you end up with a leakage from the transmitter to the receiver that can be very dispersive in frequency. That path can have significant delay, significant amplitude variation. And so what leaks to the receiver doesn't look very much like what was the original transmitter signal. And so if you take a copy of your transmitter signal to cancel it at the receiver, a simple scaling of magnitude and phase won't do because the transmitter copy doesn't look much like the interference that leaked. And so you can run a quick simulation for the channel between a pair of antennas that we tested in the lab. This is down at RF frequencies of around 1 gigahertz. A simple amplitude and phase-based cancellation, the amount of cancellation that you can get significantly reduces as you increase the bandwidth of the signal. So we started to look at this problem, and we started to see how we can do cancellation at RF that's wideband. And what you essentially need to do is you need to create delay that matches the delay in the wireless channel. But anyone who's built things at RF would know that creating time delay is fundamentally hard. Creating nanoseconds of delay is, I would actually characterize that as an impossible problem at RF. Just to get a sense of why that's impossible, delay is just created by the propagation of a wave. The wave needs to propagate by 1 foot distance to create a nanosecond of delay. So that means that your chip has to be about 1 foot in size, something like that. Now, there are techniques that you can use to miniaturize it, but you're not going to go from 1 foot to hundreds of microns of size of a delay element. And so a nanosecond of delay at RF has actually been a holy grail problem for a long time. People have looked at many ways, taking the signal into the optical domain, passing it through fiber, bringing it back to RF, accumulating nanoseconds of delay. It's just an unsolved problem. So we started to take a look at this problem, and we started to see how we can create large delays using other techniques. And so we started to look at how filters can be used to create delay. So a sharp high-Q filter also has a large delay, albeit over a narrow bandwidth. Filters are something that we've actually figured out how to build very effectively on chip. There's been a lot of work recently over the last 7-8 years, more than 300 papers published on a technique called N-path filters. It's a switched capacitor technique, which creates a high-Q second-order LC resonance without using any inductors. So now we have the ability to build filters with high quality factor, high narrowband delay, and you just need switches and capacitors. And so our idea was to take several of these N-path filters and essentially channelize the bandwidth and create the delay in each individual channel. So several N-path filters working at different frequencies, each of them you scale in magnitude and phase, and you sort of piecewise construct the self-interference channel in each of these subbands. So it's basically equalization in the frequency domain, but we're now doing this at RF, uniquely enabled by the fact that we now have the capability of building high-Q filters at RF for the first time. So using this idea, we built a full duplex chip operating at 1 point something gigahertz, and we had these N-path filters in there to do cancellation with large delay. We talk a lot about how these N-path filters are compact because they're only switches and capacitors, no inductors. The capacitors can still be pretty big, so the chip was still somewhat large because of the large capacitors that we were using to create delay, but at least it was viable to do this. And there's ongoing work elsewhere in the community on how you can further miniaturize these N-path filters. But with this approach, we were actually able to mimic the channel between two antennas that had 8 nanoseconds of delay, and we were actually able to get very wideband cancellation. So over here, the red curve is the cancellation profile that a simple amplitude and phase-based canceller would give. I think it had like 3 megahertz of bandwidth or something. When you engage one of these N-path filters, you got this green curve, which was 15 megahertz of bandwidth, roughly 5 times. When you had 2 N-path filters working at offset frequencies, you could actually create this blue curve, which was about 25 megahertz wide, which is 8 times wider than a conventional canceller. Yeah, question.
Is there a rough formula for how many of these N-path filters you need for a given bandwidth? Repeat the question.
Yeah, so the question is, if I want to cancel over a certain bandwidth, if I want to do a frequency domain equalization, how many N-path filters do I need for that bandwidth? So yes, there is a rough formula. It also depends on the delay of the channel. So if you have a channel with very little delay, you would need less number of N-path filters. The reason is the delay of a filter is directly related to its quality factor. So if you have a large delay, I need a high-Q filter, it's going to become narrow band. Then I need to put more of them in parallel to cover the bandwidth. So there's a relationship that links bandwidth and delay to the number of and it's independent of N-path filters. Whatever filter technology you use, bandwidth, delay, and number of filters are essentially related to each other. We also use this chip to do some live demonstrations of full duplex, where we essentially sent a 64 QAM modulated signal at roughly 15 dBm of average transmitter power that couples to the receiver, and then the chip is actually able to cancel that signal over the entire bandwidth using these multiple N-path filters. So this was the first work that we did at full duplex, and it is down at RF at about 1 point something gigahertz. We started to think about how we could move full duplex up into the millimeter wave. And the interesting thing is that at millimeter wave, there's a strong effort in co-designing your chip with the antenna, with the electromagnetics of the system. So you really want to think of the system holistically, not as a separate circuit and as a separate antenna, but you want to think of how the chip, the antenna, the circuits and the antenna can kind of work together to accomplish your objective. And the interesting thing is that when you get into the electromagnetic domain, polarization is another domain that you can use to separate signals. So you can use orthogonal polarizations for transmit and receive, and that can give you some initial isolation that allows you to transmit and receive at the same time. Now, technically, this isn't true full duplex. True full duplex means you should be transmitting and receiving at the same time in the same polarization. And the reason is polarization could also be used to multiplex data in one direction. And so while this, transmitting and receiving in orthogonal polarizations with double data capacity, you're doing it at the expense of a 2x that you could have got in other ways. But to the extent that this was our first effort in this area, and there are some benefits to doing this, we started to look at how you could transmit and receive at orthogonal polarizations. And so we built a couple of slot loop antennas with orthogonal polarizations. A pair of antennas has a limited isolation of about 15 dB. When you use the orthogonal polarizations, the isolation boosts to about 25 dB, so it gives you a little extra 10, 15 dB of isolation. Now, I know what you're thinking, 10, 15 dB isn't a massive leap forward towards 100 dB, right? So what we thought was interesting about polarization is you can use polarization as a domain to even do cancellation. So imagine two antennas with orthogonal polarization. You can introduce on the receiving antenna an extra port with the same polarization as the transmitter. What will happen is you have some leakage from the transmitter to the receiver in the orthogonal polarization, but some of the transmitter signal will leak to the copolarized port as well. At that port, we essentially place a reflective termination, which sort of reflects the signal back into the antenna, which then couples to the receiver. And if I can now control this termination, I can get this indirect path to exactly cancel the main leakage path. And you can get a cancellation that is electronically controlled, but is happening right inside the antenna as well in the polarization domain. And now you can actually start to apply all your filter design technologies to the design of this reflective termination. You can make a higher order filter, you can get cancellation over wide bandwidths, you can channelize, you can do all of that kind of stuff, but right within the antenna itself. So we did this actually, a very brave student did this at 60 gigahertz. And so we built a full duplex chip. Chip is here. You can see the little antennas here. You can see there's cross-polarized ports, there's the co-polarized port. The chip has the reflective termination on it. So you transmit out here, some of it leaks here, comes onto the chip conditions it, sends it back, then it leaks to the receiver, and you're actually getting the cancellation on the antenna, but controlled from the chip. Yeah, I mean, let me just say that this student, so millimeter wave is hard, packaging is hard, antennas are hard, doing all of this stuff in an academic research group is hard. This is a really heroic student, I have to say, who managed to get the system to work. He's at TI Kilby Labs, actually. But yeah, I mean, I think, so not to say that this is not a viable idea, but certainly doing it without the benefits of things like flip chip packaging and interposer technology, which we didn't have access to at the time, using PCB-based antennas and wire bond-based interfaces was a heroic task on behalf of that student. So as I mentioned, antennas, full duplex, 60 gigahertz transceiver, the reflective termination, an additional RF cancellation path. This was the first, and actually not only, there was another paper following up on this work earlier this year, but until earlier this year, this was the first and only demonstration of millimeter wave full duplex using silicon. We actually showed over a distance of roughly 1 meter a full duplex link with some non-zero signal-to-noise ratio. Again, heroic in my opinion. So essentially, the chip is transmitting a 1 gigabits per second BPSK signal. In the absence of the cancellation, if you look at the receive path of the chip, you're completely dominated by your own transmitter self-interference. Once you engage the antenna and the RF cancellation, the self-interference is substantially suppressed, and you start to see a continuous wave sine wave that was being transmitted towards the chip. You start to see the faint signs of life, basically. There's still a lot of self-interference, and so if you want to think of this like an eye diagram, the eye diagram is still closed. But then when you capture the data, you go into MATLAB, and then you do additional digital self-interference cancellation. You can now actually get the sine wave with 7 dB signal-to-noise ratio. Not great, again, but again, a first effort, certainly with improvements in digital signal processing, improvements in how we package the chip. I think it's actually viable to get the level of self-interference cancellation to over gigahertz wide bandwidths. More recent work, we've started to look at how full duplex can be combined with arrays. So this is a work where we're doing full duplex with a phased array. So the interesting thing about phased array antennas is on the transmitter and the receiver, you have amplitude and phase weights that you're applying to the signal to essentially form a beam that you want to point in different directions. So if you think about those amplitude and phase weights as degrees of freedom, you have n-1 technically degrees of freedom at the transmitter and n-1 degrees of freedom at the receiver. And you use these degrees of freedom to form a beam pointed in certain directions as well as to form the nulls of that beam. What we found is that if you're willing to give up a few of those beam-forming degrees of freedom, you can actually use them to cancel the self-interference at the receiver. Essentially, you're doing a near-field cancellation of the transmitter signal while still radiating a beam in the far field. Now, you do have to give up some degrees of freedom on the beam forming. So while you can still point the beam in the direction that you want, maybe you lose some of the nulls of that beam, or maybe the side lobes grow a little bit, or maybe the gain in the peak beam forming direction goes down. But if you're willing to give up a little something on your beam, you can actually suppress your self-interference at the receiver. So, this is an idea that we showed with an 8-element antenna array, again, down at the RF. This was working at something like 1 gigahertz. More recently, we have a paper coming out at ISSCC where we're combining full duplex with MIMO. So the problem with doing full duplex and MIMO is with MIMO, you have N antennas. They're each transmitting an an independent signal. And so now you have n squared cancellations to perform from every transmitter to every receiver. So the complexity of the cancellation in terms of the power consumption it would require, as well as the area that it would take on chip, starts to grow quadratically with the number of antennas. So certainly doing full duplex on anything that is massive in a MIMO setting is extremely challenging. So we looked at an architecture where we could sort of share some resources in the cancellers across different MIMO paths, particularly the delay that we were generating, so that we could sort of more achieve an order of n growth in complexity rather than order of n squared. And this requires certain assumptions about what the leakage path looks like from each antenna pair to every other antenna pair. But assuming a certain antenna geometry, you can actually share some resources across cancellers so that the complexity is sub-order of n squared, actually sort of more like order of n. Again, sorry that I'm not presenting a lot of details. This is going to appear at ISSCC in February of 2019. This is a chip that we built, and we were able to show cancellation of both your own self-interference and what's called the crosstalk self-interference between MIMO transmitter 1 and MIMO transmitter 2 with this shared canceller architecture. So yeah, a bunch of papers, and if you're interested in reading some of these, please feel free to go and take a look at some of these references. So let me now talk about the next direction of research. At this point, and let me just do a quick check on time. How much time do I have left? 16. Oh, not bad. I should be fine. So I'd like to talk a little bit about integrated non-reciprocal components. This is a research direction that I'm quite excited about that's going on within my group. Non-reciprocal components are components where the signal travels differently in forward and reverse direction. So if you think about an isolator, that's a component that people use at the output of a transmitter to make the transmitter safe from antenna impedance variations, because the transmitter signal will go out to the antenna, but any reflection at the antenna won't come back towards the transmitter. Another example of a non-reciprocal component is a circulator, which people use to connect a transmitter and a receiver to the same antenna. So then the transmitter signal goes to the antenna signal doesn't come back to the transmitter, it goes to the receiver, so the signal essentially circulates in one direction, doesn't go in the other direction. The problem is non-reciprocal components like that, where signals travel differently in forward and reverse directions, are very hard to build. Most materials, most circuits, they're all reciprocal. To make something non-reciprocal, you have to do one of 4 things. You have to use special materials. Magnetic materials are an example. Ferrite materials, which when you apply an external magnetic field, because of the Faraday effect, they lose their reciprocity. This is how all circulators and isolators are built today. They're magnetic. You can't integrate them on chip because ferrite materials are not compatible with semiconductor processing, Also, you need a permanent magnet sitting on top of it to set up the magnetic field to make them non-reciprocal, although I should acknowledge there is work on self-biased magnetic circulators that is ongoing. So the problem with these, I mean, they're very high performance, they're just expensive, they're bulky, you can't use them in any compact form factor device, you certainly can't integrate them on chip. You could use active devices, just transistors as amplifiers are non-reciprocal. They have gain in one direction, they don't have gain in the reverse direction. But any active device will have noise and distortion just fundamentally from its active nature. The bias current comes with noise and it comes with distortion. You can actually use nonlinearity to make non-reciprocal circuits. So this is actively done in the optics community, where people use the third-order Kerr nonlinearity of optical materials to create optical isolators and optical circulators. The problem for us in the wireless domain is we need things to be linear, right? Linearity is very important for us to be able to transmit and receive signals, so this doesn't work for anything where there's actually a modulation on the signal. And so more recently, there's been a lot of interest in using time variance to create non-reciprocity. So if I can modulate the circuit or the material, if I can change some property of it in time, then it has been shown that this can become, you can create non-reciprocity and you can build isolators and circulators. And this has actually been a high impact area of research across many physical domains, not just in electronics, but optics, acoustics, with papers published in Nature and Science because of the fundamental physics implications of it. We've been very interested, well, not only in contributing to some of that fundamental work, but also in seeing how we can engineer high-performance, practical, non-reciprocal components that would be useful for wireless applications. So the first work that we did, again, comes back to this N-path filter, which is essentially switches, a capacitor, and switches, where the switches are clocked at a certain clock frequency. And essentially, as I mentioned earlier, when you clock these switches at a certain clock frequency, this structure has a resonance shape, which is very interesting in and of itself. You get a second-order LC resonance, which is quite interesting because there's no inductor in this circuit. It's a way to get an LC resonance with no L, essentially, but with switching, with time variance. What we found is that if you phase shift the switches on the left and right, then you can create a non-reciprocal phase where the signal traveling forward has a certain phase shift, but the signal traveling backward has the opposite phase shift. So we found that an N-path filter can become a non-reciprocal gyrator by introducing a phase shift between the clocks. And so we use this to build a circulator. This was the first circulator ever to be built in CMOS, which was passive. And just to give you some sense of the resultant dimensions of it, this is that chip on top of a commercial magnetic circulator. And this paper was published in Nature Comms, but also we've been actively pursuing this idea to build high-performance non-reciprocal components that are published within our own IC community. The one thing that I'm not showing here is while this circulator is 25 times smaller than the magnetic circulator is much more than 25 times more linear than our circulator. So this was a first work that showed that the idea was possible, but certainly was nowhere near useful from a practical performance perspective. But this spurred future work within my group, and it actually led to the starting of a DARPA program, a MURI program, an NSF program, all on this idea, and so we've been following up on this. We've built full duplex transceivers that use this circulator in them to interface the transmitter and receiver to the same antenna. We also extended this to millimeter wave. At millimeter wave, you want to do the switching not across capacitors, but across delay elements, across transmission lines. So we use that to build a circulator at 25 gigahertz, thinking about 5G applications. This new architecture was also published in Nature Comms, as well as at our flagship conference, ISSCC. In the DARPA program that was started based off of this work, the efforts were how can we push this circulator architecture to handle watts of transmitter power, thus making it potentially practically useful. So again, the new architecture was leveraged now at 1 gigahertz to show a 1 gigahertz circulator with more than 1 watt transmitter power handling. as well as the ability to compensate for antenna impedance variations as much as 1.85 VSWR. And more very recently, we further pushed this into the millimeter wave. We have a 60 gigahertz circulator that is being reported at the ISSCC in the February of this year. So again, many papers in this area. Please feel free to kind of look at them. I still see this as a very new area, ripe for more innovation. You know, we're a silicon chip design group. I see this as something which can really exploit innovations in optics, in acoustics to get much higher performance implementations, both at RF as well as in the acoustic domain, as well as the optical domain. So we're actively pursuing collaborations with people who are a lot more knowledgeable than us in those areas on topics of that nature in those programs that I mentioned. So last bit of thing that I'll say, I'll talk a little bit about massive MIMO wireless, where we've done some work on the RF side here, and then I'll segue into future work. Massive MIMO, I think everyone's quite familiar with this. Tom Marzetta's in the audience, so I better flip past the concept slides very quickly. The idea is to use a large number of antennas. Of course, I'm showing 2 here. That's not really very massive. But the idea is to use a very large number of antennas to simultaneously communicate with multiple users to increase the data capacity. One challenge with massive MIMO at the hardware level is the massive MIMO signal processing can only be done is very effectively done only in the digital domain, right? It's hard to do complex signal processing that you need for MIMO in analog. And so implementations of massive MIMO essentially look like generic receivers followed by analog to digital converters, basically analog to digital conversion at every antenna element so that you can get into the digital domain while preserving all of the antenna information, and then you can rock and roll in the digital domain. You can do your massive MIMO signal processing, right? And this is certainly an effective way to do that signal processing. The challenge is that all of your RF signals are now exposed to any interference that you have that is coming from the outside world, right? Beamforming that we used to do in the phased array setting allowed you to suppress interference. Now we're not doing that anymore. We're just digitizing every single antenna. And so we're now exposed to all the interference in the analog and RF domain. So this drives up even further the dynamic range that you need from your receiver as well as your analog to digital converter to handle that interference. So even aside from the need to digitize every element, it would be even more power hungry than that because of the lack of any interference suppression. And so what we've looked at is how we can implement spatial filtering at RF that still preserves all the antenna information, but just nulls out signals that might be coming from 1 or 2 directions, which is where the interference is coming from. So instead of forming beams, we're now looking at how we can form nulls, so that we can essentially pass most of the angles, but just kill a few incident angles. So, if you have one interference coming from one direction, you pass all other directions, you just kill that one interference. Or if you have a couple of signals coming from a couple of different directions, form a couple of nulls, kill those signals, but still pass all the other directions so that you can still do MIMO in the digital domain. So we focused on how we can build these sort of arbitrary spatial filters at RF that minimize the instantaneous. So the question is, what spatial filtering needs to be done here that minimizes the net instantaneous dynamic range at your analog to digital converter to essentially result in a low power implementation. So we've done a couple of generations of this. These are at lower RF frequencies. So we had a wideband system that goes from 0.1 to about 2 gigahertz, which could form a single spatial null. So now when we look at the gain of the system, we look at it across 2 axes, angle of incidence and the input frequency. So in the input frequency, you can select a particular band, but within the angle domain, you can null a particular angle. And then we extended that to form an arbitrary number of nulls. So now we can null any number of signals coming from any number of directions with arbitrary depth of the null as well angle of null placement. Of course, you have to have a large number of antenna elements as well so that these nulls are sharp enough so that you can kill a signal but then immediately come back to pass a signal that's coming at a very close in angle. So the limits of the spatial filtering would also be dictated by the number of antennas that you have. So, a couple of papers here. Feel free to, take a look at them. So with that, let me sort of start to conclude this presentation. I've spoken a lot about the stuff that we have already done. Let me talk about stuff that we are doing and aspirationally hope to do. So on this full duplex area, I'm a hardware person. We build chips. Chips are us. We essentially have been looking at stuff that we can do in analog and RF, non-reciprocal antenna interfaces such as circulators, RF cancellers, digital cancellers, some algorithms to tune cancellers. But we have an active collaboration with folks at the networking layer who essentially we collaborate with to build models of our hardware so that they can then use those models to do things like channel allocation, scheduling, power control, which basically form the basis of designing MAC layers both in a cellular and a Wi-Fi setting. And we also have an active testbed effort where we take our chips, put them on boards, connect them to USRPs, and actually try and show end-to-end kind of full duplex systems. And what we find is that on the hardware side, we actually get a lot of feedback from from the higher layers on what the open issues are that we should be trying to solve so that this stuff can work at the system level. We are also a part of the COSMOS project, which is a large effort between Columbia, NYU, and Rutgers University. As you know, at Rutgers, there's a large NSF-sponsored testbed called Orbit, which is essentially a large number of USRPs hanging from the ceiling of a large room. And this new testbed effort is particularly exciting because we're now endeavoring to build a testbed that is now city scale. So it's actually outdoors. It's on lampposts. It's on buildings. It's basically imbued with all the vagaries of wireless communications. The other exciting thing from my perspective is this is really focusing on commodity hardware. To a large degree, the COSMOS project is looking at emerging 5G technology. So we're deploying millimeter wave, we're deploying full duplex in this test bed, and these are really experimental systems. So it allows us to essentially take things that are really not working and kind of put them out there to essentially get a better sense of what it takes to actually get things to work at the system level. So that's sort of my, as a hardware person who specializes in building things that barely work, that's my interest in this project. We're also part of COM Center, which is this large SRC DARPA center that's head out of UC Santa Barbara and Berkeley. This is looking at terahertz. So, although this is a terahertz circuit seminar, I've mostly presented millimeter wave. We've done some work at 200 and 300 gigahertz in the past within my group, but really large efforts on terahertz and both circuits and systems are really more kicking off with this center that was recently awarded. It's a large center, as I mentioned, led out of Santa Barbara and Berkeley, but with participation with many other institutions, including NYU. NYU Wireless is I think it's leading the system effort in this center. So this is an exciting new direction that we're looking at. Here, we're looking at building things at hundreds of gigahertz. We're looking at using other semiconductor device technologies such as indium phosphide, gallium nitride. Most importantly, from my perspective, we're looking at how we can heterogeneously integrate indium phosphide and gallium nitride with CMOS to enable these kinds of terahertz systems. We also have an effort on electro-optical systems within my group. There are a couple of DARPA programs that we're working on where we're looking at how we can build electronics to interface with optical systems for applications such as LiDAR and sensing. This is a concrete piece of work that we recently did in that space. It's essentially a PLL for a FMCW modulated laser for LiDAR. So this PLL will modulate a laser and chirp the laser frequency. Essentially, the innovation in this particular PLL is you need a large optical delay to sense the rate of the chirp so that you can close a feedback loop around it. Using conventional architectures, you end up needing nanoseconds of delay in the optical domain, which takes a lot of area and is significantly lossy. I think we spoke a little earlier about the challenges of true delay, which is present both at RF and at optical frequencies. This was a PLL architecture that reduces the amount of delay that you need by a factor of 10 and also substantially suppresses the spurs that you get in the final chirped output. So about a couple of months ago, we actually demonstrated this PLL working with the optical chip and with the laser. This is actually an image that we were able to take with a benchtop LiDAR system that we built. This was actually two sort of gears that were sort of attached to each other with a certain offset, and you can see the slight color difference between them, showing the depth perception of the LiDAR system that we built based on the bandwidth that we were able to modulate the laser. So that brings me to the end of the talk. Hopefully I gave you a snapshot of the kind of stuff that we've done in the past, as well as the ideas that we're looking at for the future. Thank you for having me, and I'm happy to take any questions that you might have.
Wow. What a terrific talk. Are we on? Hello? What a terrific talk by Professor Krishnaswamy. That was amazing.
Thank you.
What a depth and breadth. You really are taking analog circuit design in chips and bringing new ways of cancellation, new devices that we didn't think could be made at RF, and you're doing it at millimeter wave. This is the key to the future devices. These kinds of techniques are what companies are relying on you and your students to do. Let's give them another round of applause. That was amazing.
Thank you very much.
Just amazing what you've done, and we're really glad to be working with you. Questions for Professor Krishnaswamy? Surely we have some questions about this breadth of work. Any questions? I've got a question if no one else does. So you're making these devices in silicon. It takes a long time to get the circuits fabbed. Then you have to test them. It's hard to test, especially up at millimeter wave. How do you and your students deal with it? What are your plans? How do you do the research to kind of bake in all these delays? Because students have to get theses. Your sponsors want the results. Maybe tell us a little bit about how you do this and how the students in your lab work.
Yeah, I mean, I have to say, actually, I don't have a good answer that makes that process easy. I have to say that what we do is a very unforgiving world for a couple of reasons. So as you mentioned, the cycles associated with this research are long. It takes, we focus a lot on the idea. So it takes firstly 6 months to essentially have a new idea, 6 months to a year to have a new idea, to be able to do theoretical analysis that demonstrates a benefit of that idea over the conventional techniques. Then you have to do the circuit design. Maybe that's a couple of months. Chip takes a couple of months to fab, takes several months to do measurements. So the life cycle of a project is certainly of the order of 2 years before you actually have something working. That's not counting publication. So that is a challenge of our field. The second aspect of that challenge is you don't get 2 shots at this. You send a chip out for fabrication, and then on that day, that deadline, 5 p.m., what you send is what it is. You can't essentially call up a foundry and say, hey, I made a mistake. Could you accept this change to my layout instead? So we actually had a chip recently that we're able to coax it to work, but it has a severe challenge because of a little simple, silly mistake that a student made in that has nothing to do with the intellectual idea of the chip. And I was telling the student that there are a million ways to screw up a chip. There's only one way to kind of get it right, and that's what basically makes this area hard. So I'm just repeating those challenges. There is no magic bullet answer to this, but I will say the kind of things that we do is we try to stick as much as possible to one process technology so that we build up infrastructure in that process technology, and we can reuse components, circuits, IP blocks that have been developed within the group. So we try not to jump from one technology to another, because every time we do, it takes several years to kind of build up that infrastructure again. And a second key thing, I think, is essentially having students pass on knowledge on things that would never make it into a paper, like scripts that we use for measurements, or things that you need to do to get a chip to work. We rely on generations of students who essentially kind of pass that on, and that's one of the reasons why I put that slide on the alumni particularly. Even though they've been graduated and they've gone, we still see their influence within the group, because the number of times I hear that student who got that full duplex chip to work, the number of times I hear Tolga did it this way, and he showed me how to do it. So you still feel their influence several years later.
That's remarkable. What are the processes you're focusing on right now? Is it 65 nanometer CMOS at Foundry A and silicon insulator at Foundry B? Can you tell us?
Absolutely. So, and that's a good intellectual question as well. So if you're at RF, sub 6 gigahertz, we stick to 65 nanometer CMOS, even though the world has scaled down way below that.
Is that with TSMC or
it's with TSMC, and for a lot of the millimeter wave work, because some of these ideas like stacking exploit some things that you can do with SOI CMOS, we use 45 RF SOI from global foundries. We're fortunate to be supported by them in doing that research. They actually are also supporting us to do 22 nanometer fully depleted SOI based circuit design these days. The thing about process technology is it's an interesting question because I would say that to a certain degree, beyond maybe 45 or 32 nanometer CMOS, you don't see benefits from the RF by scaling. So the transistors, while they are fast down at the device, once you add all the parasitics, you're not seeing significant improvements in speed. So I'm not really sure pure RF performance like millimeter wave output power, millimeter wave efficiency, amplifier noise figure. I'm not sure going anything below 45 nanometer SOI, CMOS, RF SOI, you're not going to see major benefits there. But of course, the digital signal processing will benefit and will scale. So you have to actually think about, what's beneficial from the system as a whole, where you might not be getting, you might actually be taking a hit from the RF perspective, but the benefits from the digital side are enough, or even the mixed signal side are enough to dictate scaling. So I think that's a question that industry as well, with every new generation of product they grapple with, whether it's worth it to scale. Certainly, that's only talking about performance. When you talk about cost per transistor, that's just increasing over time. There's also a question of how much silicon cost actually eventually contributes to overall solution cost. At millimeter wave, it's not just the chips, the packaging is expensive, sure. Millimeter wave testing is expensive, so it's a complex multidimensional problem. But from our perspective, we have this added thing about trying to maintain the infrastructure within the group so that we're not reinventing the wheel.
Well, that's remarkable, very inspirational. Congratulations, Harish. We have something to present to you. I'll ask Professor Ivan Selesnik to come join me to your right. We have a presentation. Just bring it up in the packages. Yeah. So we have to present to you on behalf of this wonderful seminar. You can go on the other side if you're okay. Oh. Yeah, here we go. In commemoration of your great talk, let's give Professor Harish Krishnaswamy a great hand. Thank you very much.
Thank you.
All right. Thank you all for coming.